the relation between the planetary radius and the mass. And as you can, the figures are showing the three dashed lines, which is theoretically expected mass radius relations for the pure water planet and rocky planets, and I think iron-rich planets. And as you can see, for smaller planets, the so-called super Earths, the such a mass radius relations of the super Earths can be well explained by the rocky composition. So we can interpret this agreement that many super Earths typically have the uh, rocky core without thick atmosphere. On the other hand, so if we see the larger planets called sub-Neptunes, so so basically the pure water even the pure water mass radius relation cannot explain the radius, so we must need some volatile component to explain such large radius. So it causes issue to diagnose the core compositions. So for example, we can explain the mass radius relations of the certain sub-Neptune by assuming the rocky core surrounded by hydrogen-rich envelope, but we can also consider some icy core surrounded by more heavy steam envelope. So basically, if the planet has too low density or too large radius, so the planetary density alone cannot tell us, so cannot uniquely determine the possible core compositions. But we can expect these two scenarios have the pretty different compositions in the atmospheres. So I think one of the motivations of the atmospheric observations for sub-Neptune is to distinguish such a rocky world scenario and icy world scenarios. But this is also not easy. So because the atmospheric observation is in general not easy for sub-Neptunes. So especially in the prior to the JWST eras, the many observations reported the very flat featureless spectrum. This figure shows the example of the transmission spectrum of the GJ1214b, which is the focus of today's seminar. So this paper, the credibility to 2014, observed this planet with the bunch of the multiple tranche observations to get the very precise transmission spectrum, and they found that the spectrum is too flat compared to both the solar composition atmosphere or hydrogen-rich atmosphere, in other words, and the steam atmosphere purely made of the water. So this actually this kind of the flat spectrum is not unique to this planet. The other sub-Neptunes like GJ436b and other the planets are also showing the similar feature spectrum. So the third one may not be the sub-Neptune because the mass is similar to the Neptune, but radius is similar to the Jupiter. But anyway, such a flat spectrum is pretty common for low mass planets. And people usually interpret such a feature spectrum as a consequence of the presence of clouds in the upper atmospheres of the planets. So if the cloud is the optically thick, the cloud or hazes exist at the higher, the very upper atmospheres, so so they mask the lower atmosphere to mute the spectral features of the gas molecules. For example, this is one example. So if we assume the clear atmosphere, we can expect a lot of the spectral feature coming from the water, the CO2, methane. But if we include the clouds, many of the such spectral features are muted by the clouds. So because this is a low-key world discussion, so I would like to briefly introduce why the cloud and hazes matter. The understanding the cloud and hazes is important. So For instance, this figure is a famous one, where the JWST media observations detected very bright thermal emission at the CO2 band for the TRAPPIST-1b, the very famous rocky planet. And originally so basically suggested that such a bright the thermal emission is the evidence of evidence for the absence of the thick atmospheres on TRAPPIST-1b. So because if the planet has a very thick atmospheres, the heat redistribution from the day side to night side is very efficient, and the day side cannot emit such a strong thermal emissions, and absorption by CO2 further reduce the brightness temperature in this wavelength. So basically this observation originally strongly suggested that this TRAPPIST-1b is almost bare rock. But the subsequent study suggested that the thick CO2 atmosphere might be still okay-ish to explain the TRAPPIST-1b. So if the atmosphere is veiled by thick haze layers, so this is because if the atmosphere is very hazy, the haze can produce a temperature inversion. So if this temperature inversion is present, so the CO2 features can be observed as an emission rather than absorption. And CO2 absorption elevates photospheric pressure to upper atmosphere. And if the atmosphere is cloud or haze free, the upper atmosphere is colder. So basically, the CO2 absorption always makes the planet more faint. But if the temperature inversion is there, the CO2 absorption rather makes the planet brighter at CO2 band. This process may still explain the TRAPPIST-1b. So even if the thick CO2 atmosphere is present on the planet. Another example is I think several people are using the JWST to obtain the thermal phase curve for the rocky planets to assess how much the atmosphere is present on the planet. So this figure shows an example of how the thermal phase curve depends on the amount of the atmosphere on the planet. So if the planet is the bare rock, so the theory expects that the very large amplitude in thermal phase curve because the heat redistribution from day side to night side is very, very inefficient. And if the planet has a thick atmosphere, so because heat redistribution becomes efficient, so the amplitude or the contrast between the day side and the night side temperature becomes smaller. So such amplitude of the phase curve can tell us how much the atmosphere may be present on the rocky planets. But the atmospheric cloud and hazes may also complicate this picture. So this figure shows the example of the phase curve, the theoretically calculated thermal phase curve, but including the photochemical hazes in their simulations. So the Steinleck et al. 2023 showed that if the atmosphere is veiled by thick haze, the haze also acts to enhance the amplitude of the phase curve. So by efficiently absorb the stellar light at the day side. So this potentially causes a degeneracy between the amount of atmosphere and atmospheric haziness. So in the context of the rocky world discussions, so it is still vital to understand how the cloud and hazes are formed in exoplanets in general. So going back to the GJ1214b, so this planet is probably one of the typical sub-Neptunes, whose composition, the mass radius relation can be explained both either the rocky core scenario or the icy core scenario. So therefore the people and this system is present close to the solar system. I forgot the exact distance. But anyways, this planet system is and this planet is also orbiting around the small M-dwarf. So this planet is one of the most the suitable the planets that is the most suitable for atmospheric characterizations. So the people try to study the atmospheric compositions over the decades. But as I showed, this planet is known to show a very beautiful flat line. So during my PhD era, I devoted the most of my PhD time to explain this flat line. So this flat line basically suggests the presence of very thick cloud or hazes in the atmosphere. So now the JWST is there, but the JWST is still struggling to get the very definitive conclusion about this planet. So this figure shows the transmission spectrum observed by JWST MIDI, and they found that the MIDI JWST MIDI spectrum is still consistent with a flat line. So we might see some kind of bump around here, but basically to explain the overall spectrum, the flat line is still the best solution. So until the last year, so there were no competing molecular features detected for this planet. So today is I'm going to discuss about the recent observations in the middle wavelengths. So because this wavelength is probably maybe the most interesting range, because previous modeling studies predicted the prominent spectral features of CO2 or CH4 in these wavelengths. I think that so this is the figure taken from the Peter Gauss papers that interprets the HST spectrum along with the JWST MIDI spectrum. And so their best fitting model still shows some noticeable feature of the methane and CO2, which makes the observation for this wavelength range promise interesting. So in this talk, I'm going to talk about the recent JWST observations for this wavelength coverage. So so today's talk is going to use the JWST results for GJ1214b, so which was taken as a part of the median near-CAM GTO program led by Tom Green called Manatee. And in short, this program tried to observe the multiple relatively cool planets to see how the physics and chemistry happening in the atmosphere is depending on the planetary properties, especially equilibrium temperature. And one of the target is GJ1214b. So we observed the transmission spectrum of these planets using JWST near spec GS95H. And because I'm not the expert of the data analysis, so let me move on to the result parts. So this is a near spec transmission spectrum of GJ1214b, and we tested the two different independent pipelines and to make sure the consistency between the different pipelines. And we also confirm the consistent results between the. By the way, sorry. So we observed the two transits for this planet, and we confirm the consistent the result for the spectral shape between these two digits. And so basically the observed transmission spectrum looks not completely flat. So especially, so we can see some bump around 4.3 micron, which looks to be consistent with the CO2. And there are some wiggles around 3.3 micron, which might be consistent with CO2. Yep. So basically, we observed the non-flat spectrum. So for this planet. So to interpret the new JWST data, so we worked on the forward modeling. So So we assume the atmospheric aerosols of this planet is a photochemically produced particles, so-called hazes. So we compute these atmospheric temperature structures using a radiative convective equilibrium model. So we use my own the microphysical haze model to calculate the haze vertical profiles for the bunch of the haze production rates and eddy diffusion coefficient. And we also use the Vulkan to perform the photochemical calculations to predict the chemical profiles for the variety of the atmospheric metallicity, sheet ratio, Kazumasa. So in total, here is an example of the simulated temperatures, particle, and haze profiles. So we constructed the grid of the 200 the photochemistry and more than 2000 haze profiles for a variety of the metallicity, the sheet ratios, haze mass flux, and KZZ to to investigate what kind of the atmospheric parameter can best explain the data. And we then use the chimera code to calculate the transmission spectrum, and we use the pi-multiness to calculate the posterior distributions for each parameter. And here is the median model spectrum compared with JWST near spec data, along with previous HST data and JWST MIDI data. And the model spectrum reasonably explains the existing data. The model also produces a CO2 feature around 4.3 micron, and the HST in the HST region, the spectrum is almost flat, and the flatness of MIDI spectrum is also seen in the theoretical model. And one interesting result is so this model data comparison suggests extremely high atmospheric metallicity, which is about 3,000 times higher than the solar value. But we should be cautious. So because so basically haze property is very uncertain for exoplanetary atmospheres. So one big uncertainty regarding exoplanetary hazes is their optical properties. For example, that this picture is showing the experimentally produced haze analogs using the RGB colors, and depending on the atmospheric metallicity used for the haze ingredients and the temperature in the experimental setup. So this study shows the variety of the color or the optical constant in other words. So also some people suggested that the soot, like the black carbon like materials produced from flame chemistry, may also represent the exoplanetary hazes. And I recently suggested that the exoplanetary hazes may also resemble the diamond, in particular the so-called the chemical vapor deposition diamonds. So this topic is a bit different from today's one. But let me briefly introduce this the why the diamond may be expected, because I like this topic. So if you Google how to produce diamonds under low pressures, so you can find one technology so-called chemical vapor deposition, or CVD. So this technology utilizes the hydrogen and carbon mixture, the gas mixture with the hydrogen with a trace amount of the methane or carbon bearing species as the ingredients. And this technology use such the hydrogen methane mixtures in the hot temperature, the hot environment, typically around 1,000 Kelvin, under the high energy environment, like the experimental setup where the hot filament is inserted or some high energy source is inserted to produce atomic hydrogen. So this environment is actually very similar to exoplanetary atmosphere. So giant planets have the hydrogen-rich atmospheres. The carbon abundance is not very high, and temperature is high, and stellar UV photons drive the efficient photochemistry to produce atomic hydrogen. So last year, so I incorporated the theory of such CVD diamond synthesis in the haze model to investigate under what conditions the haze composition might be the CVD diamond. And actually, at wide range of the phase parameter space, the haze composition can be the diamonds. So I can talk about this topic one more 1 hour, but I stop here. So because this is a bit different topic, so please take a look at the paper if you get interest. So anyway, the key message of this slide is the haze optical constant doesn't matter. So for example, this figure shows how the spectrum is different if we assume different haze optical constants. The black carbons like soot more efficiently flatten the transmission spectrum, and more the optical constant like titan solene more produces a more wavelength depending pattern with some spectral feature coming from some CH bond within the condensed organics. So with concerns, our inference for the GJ1214 being observations may be depending on such a haze optical constant. So we repeat this model data comparison. So for the publicly available haze optical constant as much as possible. And the good news is, so basically, all haze models or all haze optical constant tested here consistently suggests the extremely high atmospheric metallicity, namely about 3,000 times higher than solar value. So we are confident that our inference regarding the atmospheric metallicity is robust to the uncertain haze optical constants. So here is the corner plot showing the posterior distributions for each atmospheric parameter. And we also test this some atmospheric model that include a more agnostic the aerosol model. So for which we parameterize the haze opacity as a simple power law function without yeah. And so basically, it's all model configuration tested here consistently suggests atmospheric metallicity as high as about 3,000 times the 3,000 solar value, or at least the value higher than about 1,000 solar value. So based on the current JWST results for this planet, so we suggest that this planet very likely has the extremely metal-rich atmosphere. So the metallicity higher than 1,000 is surprising because, so for instance, if we take a look at the vertical chemical profiles, in the vertical chemical profiles in the median atmospheric model. So we can see the abundance of the CO2 or methane or CO is higher than the hydrogen. So basically, the atmospheric main constituent is not hydrogen, but the heavy molecules like CO2 or CO. So in the left panels, the hydrogen is actually the photochemical product produced from the photodissociation of the water followed by the recombinations of the hydrogen. So basically our observation suggests that this planet has such a so-called metal-dominated atmosphere, which is more similar to secondary atmosphere. So by the way, as a bonus, so we also get some loose constraint on the C2 ratio, which is ranging from the 0.3 to 1. But this C2 ratio is the inference for the C2 ratio is depending on his assumptions. So we need more observations to get the competing results for C2 ratio. And let me briefly introduce why the model is so likes extreme metallicity. So one of the interesting point of the near spectrum is that so we see some noticeable CO2 feature, but we barely see the methane feature. So this is not expected because the GJ1214b is a relatively cool planet, And we expect that methane is usually the dominant carbon reservoir. So to make the CO2 feature bigger than methane features, basically we need to assume the very high metallicity because the methane abundance decrease with increasing the atmospheric metallicity, but the CO2 abundance increase with increasing the metallicity. So as you have the more metallicity, as you have more metals in the atmosphere, you get a more strong CO2 feature compared to methane feature. So this is a reason, one of the reasons why the model prefers a high metallicity scenario. By the way, the CO2 feature stronger than methane feature also prefers the C2 ratio lower than unity because if the C2 ratio is higher than unity, the methane feature becomes much bigger than the feature of the CO2 feature, which is not consistent with the current data. So also to explain the GJ1214b spectrum, so we need to assume the very high haze production rate, but previously the photochemical hazes were thought to basically the previous studies speculated that the main ingredients of the photochemical hazes are hydrocarbons and nitriles like methane and HCN. But in general, such a methane and HCN abundances decrease with increasing metallicity because the methane is converted to CO2, and the ingredients of the HCN, namely ammonia, is converted to N2. So this figure shows the column integrated photolysis rate, which diagnoses how much haze particles may form, and the higher value means more high high production rate for photochemical hazes, and as high metallicity regimes, so we can see the production rate. The photolysis rate of the hydrocarbons and nitriles is indeed low, except for the high C2 ratio. So this means the extreme metallicity of GJ1240b may seems to be in tension with the very thick haze layer in the planet. But we argue that maybe the other carbon species may be responsible for forming the photochemical hazes. So the middle and right panels are showing the photolysis rate for the CO and CO2 and some carbon bonded with sulfur, especially the OCS. And we found that at high metallicity regime, the photolysis rate of CO2 and CO2 and OCS basically increase with increasing the metallicity and potentially compensates the haze production. So our speculation is that maybe at the high metallicity, like what's suggested for GJ1214b, the haze production is different from what we originally thought. Maybe the haze formation is driven mainly supported by such CO2 and some sulfur-based species. And actually, the recent laboratory studies also suggested that if you put a trace amount of sulfur in the haze ingredients, the production rates can be noticeably higher than that's the experiment with sulfur. So maybe the oxidized carbon and especially sulfur may play a key role in forming the photochemical hazes in exoplanets. Lastly, let me discuss about what is the origin of such metal-dominated atmospheres. I think the one recently the popular the hypothesis to explain the metal-rich atmospheres on Sub-Neptune is magma-atmosphere interactions. So if the magma is present at the bottom of the atmospheres, the magma can interact with the atmosphere to deposit some volatile molecules like H2O to enrich the envelope in water. So this process can be responsible for the high metallicity atmospheres for low mass planets. But we suggest that this process is probably not not explaining the GJ1214b. So because so this process is suggested to produce a very low C2 ratio. This figure is taken from the COA 2024, which investigated how the C2 ratio, the relation between C2 ratio and the atmospheric O2H ratio varies with the variety of the the thickness of the atmospheres and some other parameters. And generally, they found that the C2 ratio can be much lower than the 0.1. But in our observation, the C2 ratio, uh, our observation suggests the C2 ratio higher than roughly about 0.3. So such a extremely low C2 ratio may not be consistent with what we suggest for GJ1214b. The Another hypothesis to explain the high atmospheric metallicity is the bombardment of planetesimals. So during the core formation, during the atmospheric formation, if the planets experience the intense bombardment of the planetesimals during the atmospheric accretions, so such a accreted planetesimal can sublimate to produce an envelope to achieve the vapor-rich or the metal-rich atmosphere. And this figure shows the population synthesis taken from the Fortuny 2013, showing how the atmospheric or envelope metallicity may be depending on the planetary mass. And interestingly, in their simulations, the metallicity gets maximized around the mass of about 10 Earth masses, which is comparable to the GJ1214b. Although the follow-up study with the detailed plant formation model is necessary, the extremely metal-rich atmospheres on GJ1214b may be the consequence of such planetesimal bombardments during the atmospheric formation. And speaking of the core compositions, so because basically according to our observations and other previous observations, the atmosphere of GJ1214b seems to be depleted in hydrogen. So this means the IC core scenario looks more consistent. So the current orbit of the GJ1214b is much inside the water snow line. So if this hypothesis, if this prediction, this interpretation is correct, the GJ1214b may originally formed beyond the water snow line, then migrated to the current orbit. And so this is the final slide. So the GJ1240b is interesting. So that planet has a very metal-rich atmosphere, but let me contextualize the GJ1240b in other sub-Neptunes, because recently the JWST observed the trans-atmospheric spectrum for multiple sub-Neptunes. So for instance, one typical sub-Neptune, GJ3417b, was found to have the metal-rich atmosphere, but the metallicity is much lower than what we suggest for GJ1214b. It's about 100 times higher than that of solar value, and that value is comparable to the metallicity of the Uranus and Neptune. And the famous TOI270d was also found to have the metallicity about 200, about a few hundred solar metallicity. This is metal rich, but still much lower than the value of the GJ1214b. But if you go to the more lower mass planets, actually some observations also reported similarly very high metallicity for those planets. For instance, for GJ3090b, whose mass is about 3 Earth mass, this planet was also suggested to have a very metal-rich atmosphere, the metallicity being comparable to the what we suggest for GJ1214b. And going to the a bit lower mass, this planet was found suggested to have the water vapor atmosphere, so the purely water vapor atmosphere. So although the sample size is still limited, and I cannot say the very strong claim about what kind of trend may be present, but one interesting hypothesis is So the the planets with mass as high as 10 Earth masses seem to have the atmospheric metallicity being comparable to Uranus and Neptune, and the more lower mass planets seem to have the more metal dominated atmosphere. So GJ1240b might be located as the boundary between such a hydrogen rich atmospheres and metal dominated atmospheres. But we definitely need more observations for low mass planets to get a more the to draw a more competing view regarding the atmospheric trends. So here is a summary of my talk. So so we observed the transmission spectrum GJ1214b using JWST NeoSpec, and we found a hint of CO2 feature, and so we performed the extensive model data comparison based on the microphysical, based on the photochemical models and microphysical models, and all four the models suggested the extremely high metallicity. This is supported by the relative strength of the CO2 compared to the methane feature, and the overall flatness of the spectrum also supports such a very high metallicity. And we tested a bunch of the assumption regarding the uncertain haze properties, and this inference is robust against such haze uncertainties. And the C2 ratio seems to be 0.3 to 1, but we still have the huge uncertainty in C2 ratio due to some the due to the current data quality and the uncertain haze properties. So we need a more observation and more better understanding on the haze, exoplanetary hazes. And extreme metallicity of the GJ1214 being potentially indicates that this planet is an icy world rather than rocky world. Sorry for that. And this planet may form beyond the water snowline, followed by the water snowline. So that's it from me. So thanks for listening, and I'm happy to take any questions.
A huge thank you for this super interesting talk. I'm really excited about this. Thank you, everyone. So without any further ado, are there any questions for the speaker? You can raise your hand using the raise hand function on Zoom, or you can write your question in the chat. I will ask a question if no one else does so. I'm giving everyone a second. Yes, Anjali.
I'll open my camera. Hopefully you can see me.
Thank you.
Thank you for the really nice talk. This is really exciting, and I think I'm still formulating my question in a way, but I was wondering, you got me thinking about like the different sources of volatiles in the atmosphere, like the atmosphere interior interactions versus like accretion. And I was wondering, is that like also from the haze perspective and the observation, are there any ways to place upper limits on the amount of water vapor in the atmosphere? For example, if it would in some way interact with the hazes and remove them, or if it would change the chemistry too much, remove the CO2?
Yeah, thanks for asking interesting questions. That's interesting. I think regarding the data perspective, probably it's really hard to put the upper limit on the water abundance, because basically the water feature is completely masked by the haze particles. So from the perspective of the haze formation, that's interesting. I think so we have some lower limit on the C2 ratios. I think one of the reason is so if you have the too low C2 ratio, basically there is no haze ingredients. So I think that we can translate such a C2 ratio to how much water is there in the atmosphere. So I think, yeah, we didn't perform such analysis, but I think if we can assume the photochemical haze is formed from the certain carbon species like methane or CO2 or some sulfur species, especially OCS, some atmospheric, I think I think that in the paper, so I showed how the photolysis rate of such a carbon bearing species is depending on C2O ratios, and basically drops to the very low value at the very low value of the C2 ratios. I think this means basically the haziness can put some constraint on lower limit on the C2 ratio, which can be translated to water vapor abundance. And yeah, I think the source of the volatiles is interesting. Yeah, in this discussion slide, I say that basically this process causes a very low C2 ratio, but this is true only if I think there is no carbons delivered to the interior of the planet. Some of the recent studies suggested that the refractory organics, like cometary organics, is the protoplanetary disk may be incorporated into the planetary interiors. So if we consider such a source of the additional carbons, it may elevate the overall C2 ratio to higher value to match the C2 ratio, what we suggest for GJ1214b.
Very cool. Thank you so much.
Super interesting question and answer. Are there any other questions from the audience? In the meantime, maybe I'll ask, just because it kind of links nicely to what we were just talking about, since you mentioned protoplanetary disk. I was wondering, and maybe you don't know this, but do you know how well constrained the age of the system is? Because if it's an M-dwarf star, I imagine maybe the age constraint on the star is not great. If you're thinking about formation processes. My toxic opinion is no one should trust M-dwarf ages anyway.
Yeah, I just remember the error bar is huge. I remember but this system is not very young. I think some literature suggests reported the age around 6 giga, I forgot.
Yeah.
Not so long one.
Because I'm wondering then if there's been more time for crazy things to happen. No, it's very exciting.
Yeah, one of the interesting point of this planet is I say the water world scenario is not consistent, but actually the radius of this planet is almost exactly the same as the pure water planet scenario.
Right.
But our observation didn't find water, and our observation basically just observed the hint of CO2, and CO2 has heavier than water, so we don't really know whether some atmospheric composition by our observation is consistent with the interior mass-radius relations. So maybe I think there are a lot of the room regarding how this planet evolves to end up with the current mass-radius relations.
Yeah, that's great. Thank you so much. Yeah. Any other questions from the audience? And feel free to write it in the chat if you're not able to unmute yourself. Anjali?
If someone else wants to go first.
Go on.
I had, this might be something that I misread on the plot. I remember you saying for the C2O ratio that it shouldn't be above 1 because of like the CO2 being important. And in the posterior plot, I wasn't sure, did some of like the edges of the posteriors go a little bit over 1? And I was just wondering, there was one that I think a pink one that goes like to 1.2 or something. And I was wondering, in that scenario, is there something else kind of mimicking the CO2, like the haze or something? I was just kind of curious what that could be.
Yeah, so in this pink model, so basically, so in the most of the models, basically we agnostically change the haze mass flux to fit the spectrum in the pink model. So basically calculate the haze mass flux based on the photochemical simulations. So then basically the higher C2 ratio is better to get the higher haze production. But as I discussed, the higher C2 ratio basically try to make the methane feature bigger than CO2. So the C2 ratio about unity is kind of some critical point where we can achieve both the very high haziness and the CO2 feature bigger than the methane feature. And actually, there is some unknown offset between the NRS1, NRS2 filters in the near spec instrument. And we needed to make such an unknown offset as an additional parameter, which can actually somehow mimic the relative strength of the CO2 to make some feature, because yeah, offset can somehow enhance artificially enhance the CO2 feature. So such a spectral feature is extremely weak. So we retrieve the instrumental offset of about 10 or 20 ppm, but such a very small offsets still cause some degeneracy, and it causes such a C2 ratio accumulated around 1, I think.
Brilliant, thank you.
Thank you for asking.
Any other questions for the speaker? Going once, going twice, final chance. And if not, I think we can say once again a huge thank you to our speaker for this excellent presentation. I will remind you all that if you enjoyed this talk and you want to share it with someone, you can send them the YouTube link that should be out soon. If you want to keep the discussion going, you can also join our Discord channel. And we look forward to seeing you next month, where we will be inviting Diego Luroceno, I don't know how to pronounce his name, I'm sorry, from ETH Zurich, who will be talking about the influence of bulk composition and lava flows on the long-term evolution of Venus. Thank you, everyone. Have a wonderful rest of your